Hello guys and girls, so I have had 3 different people ask me the same question within 24 hours, and I figured, well, it's a good excuse for me to do a YouTube video about this topic. And the question always comes down to the same thing, really. People want to know why they can't get their homemade forge properly hot, and what it comes down to is a lack of understanding of how forges work. This is gas forges, by the way. Solid fuel forges are remarkably easy to get hot, but if you want to reach forge welding temperatures in a gas forge that you've built yourself, there's actually a little bit of science that goes into getting them right, getting them efficient, and getting the gas usage as low as possible while getting the temperatures as high as possible. So I thought I would do a video that kind of goes into it, because a postbox forge like this, or a gas bottle forge like this, or even a giant triple burner sword forge like this one, like you'd see on Forged in Fire, they all work on the same principle. And so I wanted to explain how that principle works with a few visual aids, and that way you can better understand what it is you're trying to create when you build your own gas forge. But regardless of what type of forge you end up building, these are just 3 different types. There's more, and we're assuming we're just using Venturi burners here, although ribbon burners do use very similar principles to this. They're all going to have the same core features. You're going to have an outer casing, a shell, that's usually made of steel. And then you're going to have a layer of refractory that's going to be used to hold the heat. And then you're going to have the port. And the port is where you're going to, sometimes called the door, where you put your work in. And in a tunnel forge, it goes all the way through and out the other side. Bottle forges usually have a smaller door at the back and a bigger door at the front. Postbox forges traditionally have a very small door at the front and back, much smaller than you would find on any other type of forge. So these components all do the same thing. So what is that thing that they do? Well, what a forge does is it stops heat escaping it slower than the heat is put into it. Another way of wording that would be that heat goes into a forge faster than it can escape the forge. So what do I mean by heat escaping it? So probably most of you are familiar with the old gas bottle forge. It usually sits on its side, made out of an old gas bottle. Burner comes in at an angle, sometimes directly down, and you have a flat bottom and a rounded chamber. Sometimes you'll have a small door at the back, but what happens is when you light the burner, flames shoot down here, which put heat into the system. Now, heat is only going to escape the system in 2 ways. The first way is going to be out the doors. Any hole in your forge, front or back doors, is going to have heat leave it, because air, anywhere there is air likes to suck heat out of a system. It's why if our food is hot, we blow on it. We're adding more air to it, and that sucks the heat away from it. So we're pumping heat in with the burner, and air, because the holes in the forge are exposed to air, the air sucks the heat away. The other way that the heat disappears is that the refractory starts taking in and storing heat. And as it stores heat, it starts from the inside and it works its way out, heating up the refractory until it gets to the metal shell, and then it radiates off the metal shell once again into air. And the more air that's moving over the outer shell, the more the outer shell is going to pull heat through the refractory. So in order to get your forge hot, you need to have minimal exit holes and you need to have good refractory. The minimal exit holes will minimize the amount of heat that can leave through those holes, and the quality of your refractory setup is going to determine how much heat your forge can hold. So to demonstrate this concept, imagine that this bottle of Coke is our forge. And in our forge, the burner is coming in the top, and we have a hole in this forge bottle. The water in this jar is heat. So if I pour in very slowly, the heat doesn't have a chance to build up because it drains out that hole. But if I fill very quickly, I can fill up the bottle, and you can imagine if I was to continually pour more water in, I would be able to hold water in the bottle because they keep adding it in there. Heat in a forge works the same way. It's always going to be slowly leaking out. But if you haven't designed your forge right, like you've got really big doors or your refractory setup is terrible, it's going to be leaking out really, really fast. So the first trick to making an efficient forge is to make that leak as small as possible. Another thing you want to consider is that you're allowing your burner to actually work properly. So the flare at the bottom of a burner is super important because when you heat air, it expands. So we are pulling air in through the Venturi effect, compressing it, speeding it up, and then igniting it here. And when it ignites here, it needs a place to expand, which is why it needs a flare. So if your flare is right back here and your refractory sort of plugs up the opening of where your burner is, then that is going to restrict the ability for the expansion of the air. So you want to make sure that your burner goes pretty much all the way flush with your refractory, or at least if it's not flush, if it is recessed, there is enough gap in your refractory to allow for that expansion of the fire. Otherwise, your burner will not be burning as hot as it can be no matter what PSI you're running it at. Now you want to have some kind of vent for the heat to escape, which is usually your door. You'll notice that even large forge doors that can swing open and shut will usually have a small hole in them, which you'll see some flames shooting out of. This is good. You need to have some sort of vent, otherwise you will quickly lose control of the temperature in your forge. Because you're putting a lot of pressure in there and you need it to escape somewhere, but you just want to minimize it. A lot of beginners, when they make a forge for the first time, have really big open doors on the front and the back of it, and it's frankly just a recipe for all of your heat escaping very, very quickly. So minimizing the size of your exits or having a door that can close when needed, when you need to raise that temperature, are a really good way to minimize that. The other way is to have good refractory. So a good setup for refractory looks a bit like this. So as a cross section of your refractory, you'll see you've got your hollow space in the middle. Then you've got this solid line. That solid line is going to be something called castable refractory. Now, castable refractory looks like a sandy sort of substance. When you buy it, it was a powder. And when you add water to it in the right ratios, it will turn into a sort of a peanut buttery consistency, which you can mold to coat a surface. And you want a nice thick layer of at least an inch thick to be in the immediate presence of the work in your forge. So where the air gap is, you want it to meet up against castable refractory. There are different grades of castable refractory. You need to make sure that you've got the one that A, represents the temperature range that you're going to be working in, and B, is the right weight and density that you want. So when it comes to the density, there's pros and cons to both the lighter side and the heavier side. Dense castable refractory, which is my favorite, can take a lot of knocking. Because this is on the inside of your forge, it's going to be being hit by bits of steel, and flux is going to land on it, and all sorts of horrible exposure to impacts and things. So dense castable refractory is much more resilient to that sort of thing before it starts to crack. Because remember, this castable refractory is a consumable. It will eventually wear away. The downside is dense castable refractory takes longer to absorb heat and hold it. It's also much heavier if you're planning on moving your forge. Light castable refractory is much, much lighter, and it absorbs heat much, much quicker. However, it's not as durable, and you will punch holes in it and it will crack, and you'll have to replace it more often. So that's the only difference between the two, and you can choose the one that most suits your needs. Underneath the layer of castable refractory and underneath your outer shell made of metal is going to be a layer of ceramic wool or fiber wool or isa wool. You're going to find it under lots of different names. This works as a refractory just like your castable does. However, this blanket is extremely light. It's feather light, but it does a wonderful job of absorbing heat, holding heat, and insulating your forge. And it looks a little something like this. I'm not going to disturb it too much in this drawer because it is full of fibers that you really don't want to breathe, but you just cut it while wearing respiration and glasses. You just cut it with a Stanley knife, like a X-Acto knife, craft knife, and you fit it on the inside of your forge. You'll see a lot of people just have this blanket and nothing else. And that's very, very bad because when it gets hot, it releases small fiberglass fibers, which if you breathe in is terrible for your lungs. You can get a product called Rigidizer, which I recommend using anyway. And you put the Isowall on first, spray it with Rigidizer, and it will make it go from a sort of fairy floss consistency, a cotton candy consistency, into being hard. And you need to spray that on, let it air dry, and then fire it in order for that to happen. That will prevent the fibers from breaking off a certain amount. However, it does not fully protect it. You still want that layer of castable refractory covering all exposed isowall. And if your refractory breaks, exposing the isowall, you want to patch it again. And this will create an ideal bed of refractory to prevent or minimize heat loss in your forge. So now let's talk about internal volumes, because this is one of the ones that really bites a lot of people. They understand refractory, they understand burners, they understand all of that, doors and everything, but their internal volume is still massive. If your internal volume is too big, what it's like is trying to get a small heating element and dropping it into a Olympic-sized swimming pool and expecting it to be able to heat up the entire pool. It's just not going to happen. But if you were to take that same size heating element and stick it in just a bucket of water, it would heat it up just fine. And that's because the volume of air on the inside of your forge matters. Because when you run particularly Venturi burners, but also ribbon burners will do this as well, they are pumping a fuel-air mixture into your forge. And not all of it is going to be, when it combusts, it doesn't just turn into nothing. Doesn't disappear. It's going to displace the air that's in your forge. Think of it like, one thing I always like to tell people is I show them an empty pipe and I say, what's in this pipe? And they say nothing. I say, no, it's full of air. Air acts very much like a liquid, like a fluid. So if you have a forge, imagine that you have a forge with a very large internal volume. That volume is full of air. So when you blow in your fuel air mixture through your burner, it's going to push the air that was in your forge out of your forge. And when it pushes it out, it's going to take heat away with it as it leaves. And because it's taking heat away with it, it's going to cool your forge down. The smaller your internal volume of your forge is, the less displacement of air and thus displacement of heat is going to happen. And it's why post-box forges are one of the most efficient types of forges to run. The inside volume of it is incredibly small. My one, for example, has an internal cylinder of 4 inches in diameter and about 8 inches tall, and that's it. And it's got a large Venturi burner blowing straight into that, so it does not take much heat to get being added to the system to get that thing to forge welding temperatures. I'll easily get that up enough that I can start liquefying steel if I push my gas bottle up. So why am I going through all this information? And it's because I get a lot of questions about this, and the questions usually center around what PSI should I be running my forge at? Or why can't I get my forge up to forge welding temperatures? So the answer to those questions is complicated. I can't tell you what PSI to run your forge at, because the PSI at which you should run your forge is going to depend on the size of your burner. It's going to depend on the internal volume of your forge, the refractory setup, the shape of your forge, the size of your doors. All of this science matters when building a forge. So if you stick to these fixed rules, you should be fine. The first one is have the smallest internal volume of the forge as you can possibly get away with and still do your work. The second one is have the best quality refractory setup you can. The ideal, in my opinion, is 2 inches of isowall and an inch coating of hard castable refractory, dense castable refractory. And the third thing is minimize opening sizes on your forge. If you have post boxes are great because the doors are always small. If you have the means, put doors on the front and back of your forge that you can open and close to adjust the flow of egress of air coming out. You don't necessarily have to have a hinged door like some people have. You can just use fire bricks. And you see a lot of people just stick a fire brick in front of the entrance. Don't close it off fully, but close it off most of the way. And if you do those three things, you will be able to start lowering the PSI that you can run your forge at. I can't give you hard numbers because, as you have seen earlier in the video, it matters on a lot of different factors. So do those three things and you will get a forge that will run as good as that forge can possibly do. If you find that it's still not getting up to temperature, you need to get a better burner, you need to get better quality refraction, or you need to work on your internal volume because you may not need all that extra space. A lot of people think I need the biggest thing that I can get right out of the gate. And let me tell you, I do this professionally, full-time, and my little postbox forge does 90% of my work. They're an incredible thing, especially for knife makers. And the best thing about a postbox forge is that the burner flame has no direct contact with your work, which means less oxidation and better control of your atmosphere inside the forge. So hopefully you have found this helpful. If you have other issues that you're getting stuck on, I just wanted to let you know I do offer online services now where you can actually book me to answer a question, whether it's about something you're stuck on in knife making or blacksmithing. I'll do a custom video that helps explain it. I'll also review a knife of yours to show you where you can get better, what things you're doing really well, and give you some ideas for challenges for future work. And I also give business advice. So the link for that, as well as all my other links, are in the description below. Big thank you to my patrons for helping make this video possible, and I'll catch you guys all on the next video. See ya.
You tighten your belt, Orion. I'm only up because of the poison. The heavens are feeling the pinch. How does that